let's do 5 examples, okay? So related to forces or dynamics, kind of on the introductory side for high schools and colleges. So let's take a look here, okay, at these examples. So here's question number 1, okay, for us. So an ambulance of mass 1650 kilograms accelerates from 40 kilometers an hour to 110 kilometers an hour in 19 seconds. What net force did it experience? Okay, so for this example, let's take a look, okay, what is given and then what they are asking us for. So we have all kinds of information given. So mass is 6350 kilograms. And you have your initial speed, which is equal to 40 kilometers per hour. And then we have our final speed within here, which is 110 kilometers per hour. And all of that happens in a time of 19 seconds. Now they're asking us what is the net force. Well, the net force really has 2 equations, right? So if you have all the forces given, then you can sum up all the forces. Okay, so that's one equation. Or the other equation is from Newton's second law, which is just mass times acceleration. So now in this case, they don't give us direction, so we'll just assume, okay, that the direction is kind of to the right. All right, so in order to do this, I do need this information in order to come up with the acceleration. I already have mass given, so that's fine. Now, how am I going to find acceleration? Well, recall that acceleration, or the average acceleration, is equal to, v final minus v initial divided by the total time that passes by. That's what we have. Now, we do want these in SI units, and kilometers per hour is not exactly in SI units, so we can certainly convert these back. Well, hopefully, you have done these conversions enough. Okay, so kilometers per hour, so we know that there is 1,000 meters in a kilometer, and we know that 1 hour is equal to 60 minutes, and 60 seconds is equal to 1 minute. So we can do that. I'm going to do that directly, actually. Okay, so doing this so many times, okay, you'll notice that, you will see that you're going to be going between speeds, and really what you're doing is just either dividing or multiplying by 3.6. So kilometers per hour, so that whole entire unit conversion I can do actually in one single step. And you can double check for yourself. All right, so this is what we're going to have. This is now in meters per second. And now the other one is, which is 110, okay, so divided by 3.6, and this is going to be 30.5 meters per second. I'm going to keep all of those decimal places there for us. Now, once we have that unit conversion, again, you can do the unit conversion any way that you like. Now I can calculate the acceleration. So the acceleration, and that's going to be 30.5 minus, this is going to be 11.1. Notice I'm putting the bar over because those 5s and 1s are repeating. And this is over 19 seconds. So I have my entire acceleration. So let's do that. So 30 point, so a bunch of 5s minus 11 point and a bunch of 1s. All right, so we have our answer. And then divided by 19 seconds. Okay, so my acceleration is not really that quick, okay, in here. So 102, 3, 3, 9, etc. So don't round, it's an intermediate step, so meters per second squared. Try to keep at least 5 or 6 decimal places for yourself. I'll leave this on the calculator. Now, because I am asked about the net force, and I already have my mass, which is given, and on my calculator I have the acceleration, so that's this. So I just have to multiply it by mass. So if I take this answer and I multiply it, so in this case it's 6350, it's a mighty vehicle there, and that's the force that I would have. So 6498.5, okay, etc. And this is going to be newtons. Now, looking back, since it doesn't ask me to round to anything, so, I'll just kind of take a look at these. Okay, this one has 3 sig figs, and this one actually has 3 sig figs. This has 2 sig figs, this has 2 sig figs. So the minimum amount is 2, so I'm going to just round this off to 2 significant figures. And so that's going to be 6,500 newtons. So that would have been our net force rounded to two significant figures. And that is it, okay, so for this particular example. Here is the kind of second example that I want to take a look at. So this example states an object with a mass of, this is 150 grams, experiences several forces. So notice we have all of these different forces on this little mass here. So we have this particular force, so that's to the right. We have looks like it's a force of friction right here to the left. And then we have another force of friction, which is due to the air, which is also to the left. Okay, so if you do all of that, I'm going to shift this over, back up. Okay, in here, it's going to be related to that. And if I draw all of this out for myself, so notice that they're asking me, find the net force. So what I like to do is whenever these forces are provided to me, I'll try to draw a free body diagram. Okay, so we have, so it looks like 17 is the largest force. I'm going to really stretch it out there. That's 17 newtons to the right. Okay, so that's the force applied. I have a much smaller force, okay, to the left. This one is 3.5 newtons. This one is the force of friction. And then I have some air resistance. So it looks like something is moving. And this one is very tiny, 0.85 newtons, okay, to the left. So if I want to find my net force here, well, my net force is going to be the summation of all of the forces, okay, that I have. Again, if they don't give you a direction, you choose the direction for yourself. And typically you'll choose the positive direction. So here I'm going to choose it to the right. So 17 newtons minus 3.5 newtons and then minus 0.85 newtons. That's what you would have in here. So let's take that out. So 17 minus 3.5 and minus 0.85. So that's 12.65 newtons right there. That's what I have. Okay, so that would have been my net force. Now, if you want to be able to find this out again to significant figures, okay, so within here, you can certainly kind of be careful. Two significant figures is the kind of lowest amount in here, so we can round this to 13 newtons, okay, if that was necessary. All right, so that's what you would have there. For part B, okay, so that's the second component, find the acceleration. Okay, so this one's going to be a little bit easier for us to do. We do have the mass, so that mass is 150 grams. And if you convert it back to the SI unit of kilograms, it's just going to be shifting the decimal over 3 places. So that's 0.15 kilogram. And so since we have the net force over here, so it's 1265, I still have the full one. So this just goes back. So you'll have F net is equal to mass times acceleration. This comes from Newton's second law. I'm going to use the unrounded figures here. So 12.65. My mass is 0.15. And now I can solve for the acceleration. So if you divide both sides in here by 0.15, as you're going through, you're going to get exactly what the acceleration is. All right, so well, let's try it. So 12.65 divided by 0.15, and that's going to be quite the acceleration. So 84.3333, etc. meters per second squared. And again, so if I round this to two significant figures, so it's about 84 meters per second squared. Okay, so it's pretty crazy. Okay, so it's really accelerating, but that's because this mass is very tiny, right? So it doesn't have a lot of inertia as you're going through. So the smaller the mass, less inertia it carries, and it's much easier to accelerate it. So that would have been part B. Now let's take a look at part C. If initially the object was traveling at 1.5 meters per second, then what was its speed, okay, after 3.5 seconds? Okay, so this one is tying it back into kinematics for us. So we have an initial speed within here. It's 1.5 meters per second. The time all right, was 3.5 seconds. Okay, so this is going to be really speeding after that. And we want to know what the final is. All right, so well, final speed is nothing else but your initial speed plus the acceleration times the change in time. So if you substitute all of that in, this is now all actually in metric standard units, okay, so within here. So 1.5 plus, this is going to be the 84.3, I'll use the unrounded in there, and then 3.5 seconds. All right, so let's do that in. Okay, I already have the acceleration there, so I'm actually going to use it. So 84.33, etc., multiplied by, so it's going to be 3.5. And then added, so plus 1.5. So if you look at the, okay, so 296.6, etc. Again, if you round this off to two significant figures, this is going to be, 300 meters per second, okay? If you want to write it correctly to 3 sigs, you can put it in scientific notation, like so. All right, so that's pretty neat. And to be honest with you, so if you take this answer, this is I'm gonna just change it back into kilometers per hour to give you some perspective. It's over 1,000 kilometers per hour, so it's pretty crazy, how fast this is. Let's just see if they wanted, so the speed, yeah, so if they don't say anything, you keep it in SI units. All right, so those are the first two examples for you. We have a wheelchair with a patient weighing 120 kilograms, okay, and that patient, okay, is on a ramp with a 10-degree incline. The wheelchair is moving up the ramp at a constant velocity of 0.5 meters per second. Draw a free body diagram of the wheelchair and patient system considering friction and the normal force. All right, so we don't have any calculations in here. We just have basically a free body diagram. Okay, so we have this, free body diagram. The only problem that we have is that this is tilted at 10 degrees. So, if you imagine a ramp, I'm going to maybe draw the ramp over here. Okay, so if you have some kind of a ramp, and this is kind of straight up as you're going through. So what they're saying is that, this is at a 10-degree angle, okay, and it's moving in this direction, okay, as you're going through. And it's moving at 0.5 meters per second, right? Now it's moving at a constant velocity. Constant velocity means that the forces actually themselves are canceled off, right? The net force has to be zero if you're moving at a constant velocity, so there's no acceleration. So within here, I'm going to just kind of shift this back down in here, so it's kind of out of the way. So drawing all of the different forces, maybe I'll use a different color. So, we definitely will have, and let me shift this, 10%. Okay, I'll move this a little bit out of the way. So we have, our force of gravity, which is always down. Okay, so that's straight down. So this would have been our force of gravity, okay, that we have. We do know what this is because this would have been 120 kilograms multiplied by 9.8 meters per second squared. This would have been your weight. Now we can calculate what that is exactly. They just ask us for the drawing of the free body diagram, so I'm not going to actually compute this as it doesn't ask us for it. Now, the other component that we have is, of course, we have the normal force. Now, the normal force is always perpendicular to the surface. So I'm actually going to draw it off of this, okay, just so that you can see. Okay, so this is going to be pointing out, but it's perpendicular to the surface. So I'm going to do the little perpendicular symbol, which is that square. This is actually your force of normal. All right, so that's what we would have over here. Okay, so now, let's continue in here. So if there's a force of friction, okay, in here, so the force of friction, if it's moving at a straight, kind of straight up, okay, so the force of friction is going to oppose this. So it's going to be in the opposite direction of your movement. So this would have been your force of friction. So that's another one. And then finally, we are applying, right? So this must, okay, be here. So this must be the force applied. okay, which is going to be moving this along. Now, don't underestimate this force of friction, so this component, right? So there is a force of normal over here, and there is this, okay, is going to project out. So this force of friction is trying to, because it's on a ramp, it's trying to push this down a little bit. So it does have a little piece off of this, okay, which is trying to move it in this particular direction, okay, because that gravity, okay, that you would have. And that would be it, okay? So those are the forces. So force of normal, force of gravity, the force of friction, and then the applied force. And then we don't really have to calculate anything in here. This is more a visual picture for ourselves to be able to understand the forces. Here's the next example that we have. So we have a patient, okay, recovering after surgery, is being transported in a stretcher by a nurse. The stretcher has a weight of 180 pounds. The patient has a mass of 74 kilograms. The nurse is exerting a constant force such that the net force is 100 newtons. What is the acceleration of the patient on the stretcher? Okay, so round to 3 significant figures here and assume, so this we should know. If you're studying, eventually this should come up in your mind that, 1 Newton is 0.225 pounds. All right, so let's try this out. Okay, so we have a stretcher. Okay, so that's not what I wanted. Okay, so we have a stretcher right here. Okay, so let's say that it's some kind of a stretcher. Let me maybe bring it down. Now, this particular stretcher, I'll do my best here. Okay, so as you're going through, okay, so here are the wheels. Here's another wheel. So here's the stretcher there. We have a patient, okay, on top of this stretcher. Okay, so this particular patient that we have, all right, so we have kind of the patient right there. I don't know, it's kind of like this. Okay, I guess, so they're lying down. Now they're moving, right? So you have a net force here. So the net force is equal to 100 newtons. That's what they tell us in the example, so in the question. So notice net force right there. All right, so that patient is going to be accelerating at least for a certain amount of time until the net force maybe comes to 0. Now we do have, so notice, a weight of 180 pounds. All right, so that's for the stretcher. So we have a weight of the stretcher. So weight, I'll put a little s of the stretcher, which is 180 pounds. And that, of course, we can change back to newtons. So 0.225 pounds, that's equal to 1 newton. So let's just keep that for ourselves. 180 divided by 0.225. So that's about 800 newtons, okay, of force that we have. That's from the stretcher itself. Now, the mass of the patient, this is the mass of the patient, so P, this was given in kilograms, so 74 kilograms. All right. Okay, so we have that. And they're asking us for what is the acceleration. All right. Well, so the only way to find that is we're going to be using Newton's second law, F net equals mass times acceleration. Right? And we want to be able to solve for this. We don't know what that is. We certainly know what this is. This is 100 newtons. The mass itself, well, we know what the patient's mass is. Now, I found, okay, so within here, I found this in terms of newtons in terms of weight. Now, if you want to get the mass of this stretcher, then that would be nothing else but simply 800 newtons divided by, and this is going to be divided by 9.8. Now, why? Well, because the weight is equal to mass times gravity, right? So if we know the weight and we want to try to find the mass, well, we're going to divide both sides by gravity, which is exactly what I'm doing there. So I'm going to take this and divide it by 9.8, and that gives us, approximately 81.632. Again, you can keep more decimal places. This would have been in kilograms. So my total mass over here, So this mass is going to be the mass of the patient, okay, which is 74, plus the mass of the stretcher, which is 81.63, etc. I left it on the calculator, so this is not going to be very difficult for me, okay, to grab. So that's what I have there. And now I have to solve for the acceleration. Okay, so let's do that. So this is the mass of the stretcher, so plus the mass of the patient, so that's going to be 155.63 to 65, etc., multiplied by the acceleration, that's 100. If you want to solve for the acceleration, you're going to divide both sides, okay, so by this, by the mass on this side, and you're going to do it on this side as well. Okay, so this is going to get divided by that. All right, so let's do that in there, and let's see what we get. So 100 divided by 155, again, keep as many decimals as you can. I kept about 5 in there. So this is going to be approximately 0.64, I think they said round to 3 sig figs, so I'm going to just do that, and that's meters per second squared. That's the acceleration, and it's obviously in the same direction as the Fnet. And that would be it. So it's not the easiest of examples, especially because they gave us the stretcher in pounds, so we have to do some unit conversions and then find the mass itself. But that would be it for this example. Here's the last example that we have, at least for this video and practice questions. So during cardiopulmonary resuscitation, just CPR, so a healthcare provider exerts a force of 520 newtons downward on a patient's chest. Okay, so that's the patient. Okay, so we have a certain amount. Again, so free body diagrams are kind of neat. So you're going to have, so there should be some force, which is resistive force, but let's take a look here. So 520 newtons down. If the patient's mass is 58 kilograms, so mass 58 kilograms, what is the resulting acceleration experienced by the patient's chest during CPR? Neglect any other forces present. Okay, well, if we're going to neglect any of forces, then, this isn't really super realistic, because if you're going to be pressing down, there certainly would be a force, okay, which is kind of resisting you, right? So for every action, you have a reaction, but they're saying that we're going to be kind of neglecting this, mainly because I guess it makes the problem a little bit easier. So I'm going to just remove this. So that's the only force we have. So technically, this is your net force that is present. Now, there, as you're pressing down, you're obviously, not necessarily, the concentration is on the chest. So it's not like the whole body that you're pressing on the entire body. So technically, this entire mass we wouldn't really use. However, because they don't give us any other information, you can make that assumption that you can proceed on the assumption that you're going to just use this particular mass. Now, if they want the acceleration, then this isn't actually a very difficult question in comparison to some of the other ones in this video. So Fnet equals mass times acceleration. We have 520 newtons. Your mass is 58, and everything is in metric standard units, so this becomes very simple. You can just substitute all of this in. You can divide by 58, and we have our answer. So now this would have been, I guess, 8.9, 655, etc. meters per second squared that we would have in here. Now, it doesn't tell us what to round, so I'll round to the same number of sig figs. So it looks like 2. So this is going to be really just 9.0 meters per second squared. And that is it, right? That's all that you would have in here. Now, they do ask us an extra question. If the patient's body cannot absorb some of the force, then what can happen if too much force is used during CPR? So I think this is just kind of, logical. As you're pushing through, you have your chest cavity, you can certainly break it. And it has happened, during CPRs, to try to, once you're doing the CPR, if you put way too much force, you can literally break that. And especially if you have someone who's weaker, who's older or who's very young, you do have to be careful. Okay, that is it. Okay, so those are the examples. I hope that they helped you so that you can think of how to solve these style of questions. Thanks for watching. See you in a future video. Bye, everybody.